The sun burns at millions of degrees, sending an endless stream of energy across the solar system. Yet only a short distance away, space remains dark, silent, and unimaginably cold. How can intense sunlight travel through the vacuum without heating the space around it? The answer lies in the surprising difference between light, heat, temperature, and matter. Before the journey begins, please like this video and subscribe to the channel for more calm explorations of the universe. Now, let us travel into the darkness and discover why a blazing sun can exist inside a freezing cosmos. The universe appears as an immense darkness stretching far beyond every familiar landmark. Across that vast distance, stars shine like steady points of light. Galaxies gather into graceful shapes, and faint clouds of gas drift between brighter regions. At first glance, this great scene seems filled with countless glowing objects. Yet, careful observation reveals a very different reality. Almost everything between those distant lights is empty space. The bright objects attract immediate attention, but they occupy only a tiny fraction of the total volume of the cosmos. The overwhelming majority of the universe consists of regions where matter is remarkably scarce. Astronomers spend generations measuring these enormous distances. Their observations show that even neighboring stars are separated by astonishing expanses of emptiness. Galaxies contain hundreds of billions of stars, yet each star usually travels through an environment where almost nothing surrounds it. Between one galaxy and another, the emptiness becomes even greater. Matter still exists there, but it is spread so thinly that individual atoms may be separated by long distances compared with anything experienced on Earth. This broad view creates an interesting contrast. The night sky seems crowded with brilliant lights, yet the universe itself is defined much more by absence than by abundance. The glowing objects are islands surrounded by an ocean that contains very little material. That emptiness shapes almost every large-scale process in the cosmos. It influences how light travels, how heat moves, and how temperatures develop across unimaginable distances. On Earth, warmth is often associated with nearby objects. A stone resting beneath the afternoon sun becomes warm because sunlight reaches its surface. A lake absorbs energy throughout the day and releases it slowly after sunset. Air carries warmth from one place to another through constant motion. Oceans transport heat across continents through broad currents. Everywhere, familiar matter surrounds other matter. Solid ground-flowing water, moving air, and living organisms constantly exchange energy. The wider universe presents a very different setting. Instead of continuous material filling every location, enormous regions contain almost nothing at all. There are no endless oceans connecting stars. There are no vast rivers of air flowing between planets. There are no continuous layers of solid material stretching across space. Instead, isolated objects exist within extraordinary emptiness. This emptiness is often described as a vacuum. A vacuum is a region containing very little matter. It is not perfectly empty because tiny particles, atoms, magnetic fields, and light can still exist there. Even so, compared with conditions near Earth's surface, the amount of material is astonishingly small. In many parts of interplanetary space, only a few particles occupy the volume that would contain trillions upon trillions of molecules in ordinary air at sea level. Farther away between stars, the average amount of matter becomes even smaller. Such thinness changes how the universe behaves. Matter cannot easily pass warmth from one place to another when almost no matter is present. Familiar experiences begin to lose their meaning. A hand placed near a warm object on Earth quickly feels its heat because surrounding air helps transfer energy. A breeze carries warmth away from skin. Water spreads heat efficiently through movement. In empty space, those familiar pathways barely exist. Looking outward from Earth, the darkness between celestial objects reflects this remarkable scarcity. The darkness is not simply the absence of visible light. It also represents the absence of large amounts of material. Most directions through space eventually reach a distant star or galaxy, but before that light arrives, it crosses immense regions where almost nothing interrupts its journey. The scale of these empty regions is difficult to imagine using ordinary experience. Human beings naturally think in terms of rooms, buildings, mountains, or even continents. The universe extends far beyond such comparisons. Distances separating major astronomical objects are measured across millions or billions of years of light travel. Throughout much of that journey, light passes through environments containing only scattered particles. Observations from ground-based telescopes and spacecraft confirm this picture repeatedly. Large surveys of galaxies reveal delicate networks stretching across the observable universe. Galaxies gather into clusters connected by long filaments of matter. Between these structures lie enormous cosmic voids where galaxies become extremely rare. Even these voids are not absolutely empty, yet they contain far less matter than surrounding regions. The largest structures in existence therefore emphasize not crowded abundance, but remarkable spaciousness. Within individual galaxies, a similar pattern appears. Spiral arms glow with countless stars, while broad intervals separate neighboring stellar systems. Dark clouds drift through parts of the galaxy, yet these clouds themselves are astonishingly thin compared with Earth's atmosphere. Even the densest star-forming regions remain extraordinarily sparse by everyday standards. This understanding develops slowly through centuries of observation. Early astronomers map the motions of planets and stars. Later generations build increasingly powerful telescopes capable of revealing faint galaxies beyond the Milky Way. Modern observatories operating above Earth's atmosphere detect forms of light invisible to human eyes. Together, these observations strengthen the same conclusion. The visible universe contains magnificent concentrations of matter, but these occupy only a minute portion of an overwhelmingly empty cosmos. The quiet appearance of the night sky reflects this balance. Darkness dominates while scattered lights remain widely separated. Every bright star represents a distant concentration of matter, surrounded by tremendous expanses where almost nothing exists. Every glowing galaxy shines across distances almost beyond comprehension, with its light crossing vast regions of near emptiness before reaching another world. From this widest perspective, the universe becomes easier to understand as a place defined less by what fills it than by what surrounds everything within it. The great darkness is not merely a backdrop painted behind the stars, it is the dominant environment itself. Stars, planets, Moons, comets, dust clouds, and galaxies exist as isolated structures immersed within that immense vacuum. Their brilliance attracts attention, but the silent emptiness between them occupies almost all of existence, quietly shaping the conditions that allow the cosmos to remain both astonishingly beautiful and profoundly cold. Light leaves the surface of the sun and begins a journey through a remarkable environment. Unlike a traveler crossing mountains, forests, or oceans, sunlight moves through regions where almost nothing stands in its path. The surrounding vacuum offers very little material to slow its progress. Instead of passing from one object directly into another, light continues across immense distances with extraordinary consistency, carrying energy from its source into the wider solar system and beyond. Light is a form of electromagnetic radiation, meaning energy that travels as linked electric and magnetic fields. Once this idea is understood, the simpler picture becomes easier to follow. Light carries energy without needing air, water, or any other material through which to move. This property makes it different from familiar experiences on Earth. A spoken voice depends upon air. Ocean waves depend upon water. Vibrations in the ground depend upon solid rock. Light requires none of these. It travels through empty space itself. This simple fact explains why the sun remains visible from Earth despite the enormous distance separating the two worlds. Between them lies a broad region containing only a small amount of gas dust and charged particles. There is no continuous bridge of air stretching across the solar system. Even so, sunlight arrives steadily every clear day because the vacuum does not prevent its passage. The journey is remarkably direct. Every second the sun releases an immense amount of energy in every direction. Light spreads outward like an ever-growing sphere centered upon the sun. Each part of that expanding sphere carries only a fraction of the total energy, yet together the entire sphere transports the sun's power across the surrounding darkness. As the sphere grows larger, the same total amount of energy covers a greater area. This natural spreading means that sunlight becomes less intense with increasing distance from the sun. Mercury receives much stronger sunlight than Earth because it circles much closer to the source. Mars receives less because it travels farther away. The giant planets beyond Mars receive progressively weaker sunlight, still not because the sun shines less brightly toward them, but because the energy is distributed across a much larger region before reaching those distant worlds. This gradual weakening often creates an intuitive misunderstanding. It may seem that if sunlight fills space, then space itself should become steadily warmer. Observation shows something very different. The light passes through the vacuum, but the vacuum does not behave like a blanket soaking up heat. Instead, the energy continues moving until it meets matter capable of absorbing part of it. A simple comparison helps clarify the process. Rain falling through open air does not make the air become a lake. The drops continue downward until they reach soil, rivers, rooftops, or leaves. In a similar way, sunlight streams across empty space without remaining behind to warm the vacuum itself. The energy continues its journey until it encounters a planet, a moon, a spacecraft, a grain of dust, or another object. When sunlight reaches such an object, several different things may happen. Some of the light may bounce away. This process is called reflection. Snow clouds and polished surfaces reflect large amounts of incoming light. Some of the light may instead enter the material. When this happens, the energy becomes part of the object. Atoms and molecules begin moving more actively, and the object's temperature can increase. Some materials do both, reflecting part of the light while absorbing the rest. This distinction is central to understanding why the space surrounding the Sun remains so cold. The energy is present as traveling light, yet traveling energy is not identical to stored warmth. Temperature describes the energy already held by matter. Empty space contains extremely little matter capable of storing that energy. The light, therefore, continues onward instead of building up heat within the vacuum. Spacecraft provide an excellent demonstration of this balance. A satellite orbiting Earth may have one side facing the Sun while another side remains in shadow. The sunlit surfaces absorb radiant energy and become much warmer than shaded parts. Engineers carefully choose materials' reflective coatings and insulation because every exposed surface responds differently to sunlight. The surrounding vacuum itself contributes very little warming. Instead, each part of the spacecraft gains or loses energy depending upon whether sunlight reaches it. The same principle extends throughout the solar system. Asteroids rotate slowly beneath constant sunlight. One side may spend many hours facing the Sun before gradually turning into darkness. Temperatures rise while sunlight is absorbed and fall after the surface rotates away. The nearby vacuum does not preserve the warmth. It neither stores large amounts of energy nor returns that energy later. The changing temperatures belong to the solid surface rather than to the surrounding emptiness. Dust grains drifting through space experience similar conditions on a much smaller scale. A tiny particle absorbs sunlight while illuminated. It also releases energy continuously. Its temperature reflects the balance between incoming and outgoing energy rather than any warmth held by the vacuum around it. Every grain responds individually because each one interacts directly with sunlight instead of receiving heat from neighboring material. Observations across the solar system repeatedly confirm this picture. Regions directly exposed to sunlight become warmer than nearby shaded regions. Rocky surfaces, icy plains, metallic objects and clouds each respond according to their own physical properties. Meanwhile, the empty regions separating these objects remain almost entirely without stored heat. Light crosses them constantly, yet little matter exists there to absorb the passing energy. The vacuum therefore acts less like a container filled with warmth and more like a vast, transparent pathway. Sunlight races through this pathway in every direction, carrying energy outward across distances that stretch far beyond the orbit of the outermost planets. Long after leaving the solar system, that same light continues into interstellar space, where it may travel for thousands or even millions of years, before finally meeting another cloud of gas, a wandering planet, or a distant star system. This uninterrupted journey reveals one of the most elegant features of the universe. Light can connect distant regions without transforming the emptiness between them into a warm environment. Energy travels faithfully across the darkness while the vacuum remains largely unchanged. The sun, therefore, shines continuously into a cosmos where its light is everywhere in motion, yet the immense spaces separating celestial bodies remain defined not by accumulated warmth, but by extraordinary emptiness through which the light quietly passes. Temperature is one of the most familiar ideas in everyday life, yet its meaning becomes less obvious when applied to the vast emptiness beyond Earth. A warm afternoon, a cool evening, boiling water and falling snow all provide ordinary experiences that seem easy to understand. These familiar situations involve large amounts of matter exchanging energy with one another. In space, however, matter is often so scarce that the idea of temperature must be considered with greater care. In simple terms, temperature describes the average energy of the particles within a material. Particles include atoms, molecules, and other tiny pieces of matter. When these particles move more rapidly or vibrate more strongly, the material has a higher temperature. When their motion becomes slower, the temperature is lower. This definition applies equally to solids, liquids, gases, and the thin clouds of particles found throughout the universe. On Earth, this relationship is usually hidden because matter is abundant everywhere. Air surrounds every living creature. Water fills rivers, lakes, and oceans. Soil, rock, wood, and metal constantly exchange energy with the surrounding environment. Since everything remains in close contact, temperatures often become similar over time. Warm objects cool, cool objects warm, and energy flows naturally from higher temperatures toward lower temperatures until balance is reached. The vacuum of space changes this familiar picture almost completely. Since very few particles exist within much of the cosmos, there is very little material whose temperature can even be measured. This leads to an important distinction. Asking for the temperature of empty space is not quite the same as asking for the temperature of a stone or a cloud of gas. Temperature belongs to matter. Where almost no matter exists, the concept becomes much less direct. Scientists, therefore, examine different parts of space according to what is actually present. If a cloud of gas drifts between stars, its temperature can be measured because atoms within the cloud possess motion. If a spacecraft travels through interplanetary space, the temperature of its metal surfaces can be measured because the atoms within the metal vibrate with measurable energy. If sunlight passes through a region containing almost no particles, the light carries energy, but the surrounding vacuum itself does not become a warm substance in the ordinary sense. This distinction often surprises people because warmth is commonly associated with nearby sunlight. Standing outdoors beneath a clear sky creates an immediate sensation of heating. It may seem natural to imagine that the surrounding air itself is becoming warm simply because sunlight passes through it. In reality, much of the warming occurs after sunlight reaches Earth's surface. The ground absorbs energy, then transfers part of that energy back into the atmosphere through several physical processes. The air becomes warm, largely because it interacts with the heated land and oceans, rather than because sunlight alone heats every molecule directly. Without abundant matter, this familiar chain of events cannot occur. The vacuum offers almost no particles capable of storing incoming energy. Sunlight continues its journey while the emptiness remains largely unchanged. Astronomers also measure temperature using the light emitted by distant objects. Every object whose temperature is above absolute zero releases electromagnetic radiation. Absolute zero is the lowest possible temperature, where particles possess the least possible internal energy allowed by the laws of quantum physics. Nothing observed in nature has reached this limit exactly. Every star, planet, cloud of gas, grain of dust, and living organism emits some form of thermal radiation because each contains internal energy. The type of light emitted depends strongly upon temperature. Very hot stars produce large amounts of visible light and ultraviolet radiation. Cooler planets emit mostly infrared radiation, which human eyes cannot detect. Even colder objects release much longer wavelengths. Sensitive instruments carried by telescopes detect these invisible forms of light, allowing scientists to estimate temperatures across the universe without touching the objects themselves. Infrared astronomy becomes especially valuable because many cosmic objects remain too cool to shine brightly in visible light. A dark cloud drifting between stars may appear nearly invisible through an ordinary telescope, yet infrared observations reveal the faint heat released by its dust and gas. In this way, astronomers map regions that would otherwise remain hidden against the darkness. Temperature measurements also depend upon balance rather than simply the presence of energy. A planet receives energy from nearby stars while simultaneously releasing energy into space. If incoming and outgoing amounts become equal over long periods, the average temperature remains relatively stable. If more energy arrives, then leaves, temperatures rise. If more energy escapes than arrives, temperatures gradually fall. This balance governs worlds throughout the solar system as well as countless planets orbiting distant stars. Even individual particles obey these same physical principles. A lone dust grain floating through interstellar space absorbs light from nearby stars. At the same time, it emits its own thermal radiation. Eventually, these opposing processes reach equilibrium, meaning the incoming and outgoing energy become equal. The grain settles at a temperature determined by its environment rather than by any warmth stored within the surrounding vacuum. Scientists sometimes describe space itself as having a temperature of about 2 7/10 degrees above absolute zero because the entire universe is filled with the faint cosmic microwave background. This ancient radiation reaches every direction in space and provides a measurable bath of low-energy light. It does not mean the vacuum behaves like ordinary warm air. Instead, it reflects the presence of an extremely faint background of radiation remaining from the early history of the universe. Later observations have measured this background with remarkable precision, making it one of the strongest pieces of evidence supporting the modern understanding of cosmic evolution. Careful measurement, therefore, separates ideas that everyday language often combines. Heat refers to energy moving from one place to another. Temperature describes the internal energy already present within matter. Light carries energy across empty space without requiring matter along the way. Matter absorbs that energy, stores part of it, and releases it again according to the laws of physics. These processes occur continuously throughout the cosmos, whether in the blazing atmosphere of a star, the frozen surface of a distant moon, or a solitary grain of dust drifting silently between the stars. Seen from this perspective, the apparent contradiction begins to disappear. A brilliant sun may flood nearby space with radiant energy, yet the surrounding vacuum remains largely empty of matter, capable of storing that energy as warmth. Temperature belongs to the particles that receive and retain energy, not to the emptiness through which the light quietly travels. The universe, therefore, presents not a conflict between a hot star and a cold cosmos, but a precise expression of how energy, matter, and radiation interact across immense distances. The Sun stands at the center of the solar system as a vast sphere of hot plasma held together by gravity. Plasma is matter in which atoms become separated into charged particles because of extremely high temperature. Nearly all of the Sun consists of hydrogen and helium, with much smaller amounts of heavier elements. Its visible surface appears calm from a great distance, but every region within it is shaped by continuous motion pressure, magnetic activity, and the steady flow of energy. The Sun contains almost all the mass in the solar system. Its gravity keeps planets, moons, asteroids, comets, and dust moving along their paths. Deep within the Sun, the same gravity compresses matter with extraordinary force. The weight of the outer layers presses downward, creating immense density and temperature near the center. These conditions allow the process that powers the star to continue. At the solar core, hydrogen nuclei move so rapidly that some collide with enough energy to join together. This joining is called nuclear fusion. In the main chain of reactions, hydrogen gradually becomes helium. A small portion of the original mass is converted into energy. The Sun, therefore, does not shine because it burns like wood or fuel. It shines because nuclear reactions continuously transform matter under extreme pressure and heat. The core occupies only the innermost part of the Sun, yet it produces nearly all the energy that later emerges from the surface. Temperatures there reach about 15 million degrees Celsius. The pressure is so great that the plasma remains compressed despite the intense heat pushing outward. Gravity presses inward, while heated matter and radiation press outward. The Sun remains stable because these forces stay in broad balance. This condition is called hydrostatic equilibrium. It prevents the star from collapsing rapidly under its own weight or expanding freely into space. Energy created in the core does not travel directly to the surface in a straight line. The interior is extremely dense. Light particles called photons interact repeatedly with surrounding charged particles, losing direction and being absorbed and released again. A photon may move a short distance, encounter matter, and then continue in another direction. Through countless interactions, energy slowly works outward through the deep interior. This inner region is known as the radiative zone because radiation carries most of the energy through it. Although light crosses the distance from the Sun to Earth in a little more than 8 minutes, energy produced in the core may take many thousands of years to pass through the dense solar interior. The exact travel time cannot be followed for a single photon because absorption and release constantly change the radiation. Models nevertheless show that the outward movement is extremely slow compared with the final journey through open space. Farther from the center, the solar material becomes cooler and less dense. Radiation becomes less efficient at carrying energy. Large currents of plasma then begin to rise and fall. This region is called the convection zone. Hotter material rises toward the surface, releases energy, cools, and sinks again. The motion resembles circulation in heated water, though the scale and conditions are vastly different. These movements carry energy through the outer part of the sun. At the visible surface, known as the photosphere, the plasma becomes thin enough for light to escape more freely. The photosphere is not a solid boundary. It is a layer of glowing gas several hundred kilometers thick. Most visible sunlight begins its outward journey from this region. Its temperature is about 5,500 degrees Celsius, far cooler than the core, but still hot enough to produce intense visible radiation. The photosphere has a textured appearance when observed at high resolution. Bright cells cover the surface, each formed by rising hot plasma surrounded by darker lanes where cooler material descends. These cells are called granules. They change over periods of minutes as convection continually reshapes the visible surface. Their motion provides direct evidence that energy is still being carried upward from deeper layers. Dark sunspots sometimes appear within the photosphere. They are cooler than nearby regions, though they remain extremely hot by earthly standards. Strong magnetic fields restrict the usual movement of plasma, reducing the amount of heat reaching the surface in those locations. Sunspots often gather in groups and change as the sun rotates. Their number rises and falls over a cycle lasting roughly 11 years. Above the photosphere lie thinner layers of the solar atmosphere. The chromosphere forms a glowing region where jets and arcs of plasma rise under magnetic influence. Beyond it extends the corona, the sun's outer atmosphere. The corona reaches temperatures of more than 1 million degrees Celsius, making it much hotter than the visible surface beneath it. Observations indicate that magnetic processes transfer energy into this outer atmosphere. Scientists understand many parts of this heating, though the relative importance of different mechanisms remains uncertain. The corona gradually expands outward and produces the solar wind, a stream of charged particles flowing through the solar system. The solar wind is not the same as sunlight. It consists of matter rather than electromagnetic radiation, and it travels much more slowly than light. It shapes magnetic environments around planets, interacts with comets, and contributes to auroras when particles reach planetary atmospheres. Most of the sun's energy still leaves as radiation. Visible light forms only part of the total output. The sun also releases infrared radiation, ultraviolet radiation, radio waves, X-rays, and other forms of electromagnetic energy. The proportions vary with wavelength and solar activity, but the total flow remains remarkably steady over ordinary human timescales. Every second, the sun converts hundreds of millions of tons of hydrogen into helium and transforms several million tons of mass into energy. Even at this enormous rate, the sun contains enough fuel to continue its stable life for billions of years. Its present age is about 4.5 billion years, and observations and models indicate that it remains near the middle of its main period of hydrogen fusion. From the core to the corona, the sun functions as a continuous system of energy production and transport. Gravity creates the pressure needed for fusion. Fusion releases energy. Radiation and convection carry that energy outward. The photosphere allows it to escape, and the outer atmosphere adds streams of charged particles to surrounding space. The brilliant light seen across the solar system is therefore the final outward expression of processes that begin deep inside a star and proceed steadily through each solar layer. Earth travels around the Sun at an average distance of about 150 million kilometers. At this distance, sunlight arrives with enough intensity to support oceans and atmosphere and a wide range of surface temperatures. The planet does not sit inside a warm substance surrounding the Sun. It moves through near vacuum, receiving energy directly from radiation while releasing energy back into space. Its warmth develops from this continuous exchange. Sunlight reaches the upper edge of Earth's atmosphere after crossing interplanetary space. The incoming energy is not distributed equally across the entire planet at any single moment. One hemisphere faces the Sun while the other turns away. The sunlit side receives a direct flow of radiation, while the dark side receives no immediate sunlight. Earth's rotation carries each region through alternating periods of illumination and darkness, creating the daily rhythm of warming and cooling. The shape of the planet also affects how strongly sunlight reaches different places. Near the point where the Sun stands highest in the sky, the rays strike the surface more directly. The same amount of energy is concentrated over a smaller area. At higher latitudes, sunlight arrives at a lower angle and spreads across a broader surface. The energy becomes less concentrated, so average temperatures are generally lower. This geometric difference contributes to the contrast between equatorial regions and the polar zones. Earth's axis is tilted relative to the plane of its orbit. As the planet moves around the Sun, this tilt changes the angle and duration of sunlight reaching each hemisphere. During part of the year, one hemisphere leans toward the Sun and receives longer days and more direct sunlight. During the opposite part, it leans away and receives shorter days and weaker illumination. The seasons arise from this changing pattern rather than from large changes in the distance between Earth and the Sun. The amount of sunlight arriving at the top of the atmosphere is often described as the solar constant. It is not perfectly constant because Earth's orbit is slightly elliptical and the Sun's output changes by a small amount over time. Even so, it provides a useful measure of the energy available to the planet. On average, about 1,360 watts reach each square meter of surface facing the Sun directly at the upper atmosphere. Since Earth is spherical and only one side is illuminated at a time, the average amount spread across the whole planet is much lower. Not all incoming sunlight remains within the Earth system. Clouds, ice, snow deserts, and the atmosphere reflect part of it back into space. The fraction reflected is called albedo. Bright surfaces usually have a high albedo, while darker surfaces absorb more energy. Fresh snow reflects much of the light that reaches it. Dark ocean water absorbs a larger portion, especially when the Sun is high. Earth's average albedo helps determine how much solar energy becomes available for warming. The absorbed energy does not raise every part of the planet to the same temperature. Land water, ice vegetation, and clouds respond differently. Rock and soil often warm quickly under sunlight and cool quickly after sunset. Water warms more slowly because energy is mixed through a greater depth and because water requires substantial energy to change temperature. Oceans, therefore, store large amounts of heat and release it, gradually reducing temperature changes in nearby coastal regions. Earth's surface also has a wide range of colors, textures, and chemical properties. Dark forests absorb sunlight differently from pale deserts. Ice sheets reflect more energy than open ocean. Moist soil changes temperature differently from dry sand. These variations produce local patterns of heating that influence winds, clouds, and the movement of water. The planet's warmth is therefore not a single uniform condition, but a shifting field shaped by sunlight and material properties. Once the surface absorbs solar radiation, atoms and molecules within the material gain energy. The ground ocean or ice then emits thermal radiation. Because Earth is much cooler than the Sun, it releases most of this energy as infrared radiation rather than visible light. Infrared radiation leaves the surface continuously during both day and night. Some escapes directly into space, while some interacts with gases and clouds in the atmosphere. Over long periods, Earth's average temperature depends upon the balance between absorbed sunlight and outgoing infrared energy. If the planet absorbs more energy than it releases, it warms. As it warms, it emits more infrared radiation, which tends to restore balance. If it releases more energy than it absorbs, it cools and emits less. This response produces a broad equilibrium, though the climate can change when the balance is altered by variations in sunlight, surface reflectivity, atmospheric composition, or other influences. The contrast between Earth and nearby empty space is therefore not caused by distance alone. Both occupy nearly the same region of the solar system and encounter the same general stream of sunlight. The difference lies in matter. Earth has a solid surface, liquid oceans, clouds, and gases capable of absorbing energy. Empty space has almost none. The planet gathers a small portion of the sun's expanding radiation and converts part of it into internal motion within matter. A surface in direct sunlight can become warm even when the surrounding vacuum remains cold. This occurs on Earth, on the Moon, on asteroids, and on spacecraft. The exposed material absorbs energy while nearby emptiness does not. On Earth, the effect becomes more complex because the planet rotates, reflects light, stores heat in oceans and land, and circulates energy across its surface. Seen from far away, Earth is a small sphere, intercepting only a tiny fraction of the energy released by the Sun. Much of that fraction is reflected, and the rest is eventually returned to space as infrared radiation. Between arrival and departure, however, the energy remains long enough to warm rock, move air, melt and freeze water, and sustain the planet's changing climate. Earth is warm, not because space around it is warm, but because matter on the planet repeatedly absorbs, stores, moves, and releases the sunlight that reaches it. Earth's atmosphere begins where the solid and liquid surface gives way to a thin envelope of gases held by gravity. This envelope does not receive sunlight as a single uniform layer. Energy enters from above, passes through changing densities of air, reaches clouds and the ground, and then moves again through the atmosphere in several forms. The warming of the planet depends on this continuous exchange between sunlight, the surface gases water, and moving air. Most visible sunlight passes through the atmosphere without being absorbed completely. Some wavelengths are scattered by molecules and tiny particles. Shorter, visible wavelengths scatter more strongly, giving the daytime sky its blue appearance. Some sunlight is reflected by clouds or by bright surfaces below. The remaining portion continues downward and is absorbed by land, oceans, ice vegetation, and buildings. In this way, much of the lower atmosphere is warmed indirectly from below rather than directly from the sun. The ground responds quickly when sunlight reaches it. Soil, sand, rock, and paved surfaces absorb radiation and convert it into internal energy. Their atoms and molecules move more actively, so their temperature rises. The warmed surface then transfers energy to the air touching it. This direct transfer is called conduction. Air molecules collide with the warmer surface and gain energy, though conduction alone affects only a shallow layer because air is a poor conductor compared with many solids and liquids. Convection carries the warming farther upward. Convection is the movement of energy through the motion of a fluid, and air behaves as a fluid. Air near a warm surface expands, becomes less dense and rises. Cooler, denser air moves downward to replace it. These rising and sinking motions mix the lower atmosphere and create currents that transport heat away from the ground. Over dry land on a sunny day, convection may become strong enough to produce broad columns of rising air. The ocean behaves more slowly. Sunlight enters the upper water and is absorbed across a depth that depends on clarity and wavelength. Wind and waves mix the warmed surface water downward. Currents carry stored energy over great distances. Because water can absorb a large amount of energy while changing temperature, gradually the oceans act as a major heat reservoir. They reduce rapid temperature changes and release warmth long after the original sunlight has been absorbed. Evaporation moves energy in another form. When liquid water changes into water vapor, it takes energy from the surface and carries that energy invisibly within the gas. The water vapor may travel upward or sideways before cooling and condensing into droplets. During condensation, the stored energy is released into the surrounding air. This movement of hidden energy, known as latent heat, plays a central role in clouds' rainfall as storms and the wider circulation of the atmosphere. Earth's surface continually emits infrared radiation. The strength of this emission depends on temperature, so warmer regions generally release more energy than cooler ones. Infrared radiation rises from deserts, forests, cities, oceans, and ice. Certain atmospheric gases absorb some of this outgoing energy. These gases include water vapor, carbon dioxide, methane, nitrous oxide, and ozone. After absorbing infrared radiation, they emit radiation in many directions, including upward toward space and downward toward the surface. This process is called the greenhouse effect. It does not prevent energy from leaving Earth, and it does not create energy. It changes the altitude and temperature from which much of the planet's infrared radiation finally escapes to space. Without naturally occurring greenhouse gases, Earth's average surface would be far colder. Their presence keeps the lower atmosphere and surface warm enough for stable liquid water across large regions. Clouds influence the energy balance in two opposing ways. Their bright upper surfaces reflect incoming sunlight, reducing the amount absorbed below. At the same time, cloud droplets and ice crystals absorb and emit infrared radiation, slowing the loss of energy from the surface and lower atmosphere. Low, thick clouds often produce strong cooling through reflection, while high, thin clouds can allow much sunlight through and still reduce infrared loss. The overall effect depends on cloud height, thickness, composition, location, and time of day. The atmosphere also redistributes energy across the planet. Uneven heating between equatorial and polar regions creates pressure differences. Warm air rises in some regions while cooler air sinks elsewhere. Earth's rotation turns these motions into broad circulation patterns. Winds carry warm air toward cooler latitudes and return colder air toward warmer regions. Weather systems form within this moving structure, transferring heat and moisture over hundreds or thousands of kilometers. Mountains, coastlines, forests, deserts, and ice sheets shape these movements. A mountain range forces air upward, causing expansion and cooling. Moisture may condense on one side while drier air descends and warms on the other. Coastal winds develop because land and water change temperature at different rates. Vegetation affects evaporation and surface reflectivity. Snow and ice preserve cooler conditions by reflecting sunlight, though melting can expose darker surfaces that absorb more energy. At night, the surface continues to emit infrared radiation, even though incoming sunlight has stopped. Land often cools quickly, especially under clear and dry conditions. Air near the ground then loses energy to the cooler surface. Under calm conditions, this can create a temperature inversion with colder air below warmer air. Clouds and water vapor reduce nighttime cooling by emitting infrared radiation downward, while clear skies allow energy to escape more efficiently. The lower atmosphere, therefore, acts neither as a simple blanket nor as a direct furnace. It is a moving, changing system that absorbs, emits, reflects, and transports energy. The surface gathers much of the incoming sunlight, and the atmosphere carries that energy through conduction, convection, radiation, evaporation, condensation, winds, and clouds. Oceans and land store energy for different lengths of time, while gases control how efficiently infrared radiation leaves. Earth remains warm because these processes delay and redistribute the departure of solar energy. Every amount of energy absorbed at the surface eventually moves onward, either into the air, into water, into the ground, or back towards space as radiation. The atmosphere does not isolate the planet from the cold surroundings. It regulates the path by which energy passes through the Earth system, creating the layered and shifting temperatures that define the living surface. Between Earth and the neighboring planets lies an immense region that appears empty to ordinary sight. No blue air fills the distance, no continuous ocean of gas connects one world to another. Instead, the solar system contains a very thin mixture of charged particles, neutral atoms, microscopic dust, magnetic fields, and radiation. The amount of matter is so small that the space between planets behaves very differently from any environment found near Earth's surface. This region is called interplanetary space. It extends outward from the Sun, through the paths of the planets and far beyond them. Although it is not perfectly empty, its density remains extremely low. Near Earth's orbit, the solar wind usually contains only a few particles in each cubic centimeter. The number changes with solar activity, distance from the sun, and local disturbances, but even a relatively dense stream remains extraordinarily sparse compared with ordinary air. At sea level, every cubic centimeter of air contains an enormous number of molecules. These molecules collide continuously, passing energy from one to another. Such collisions allow air to conduct heat and support convection. In interplanetary space, particles are separated by much larger distances. Collisions occur far less often. Heat cannot spread through the region in the familiar way because too little matter exists to carry it. The solar wind provides most of the particles found there. It flows outward from the sun as a stream of electrons, protons, and heavier charged particles. These particles move rapidly, often traveling hundreds of kilometers per second. Their high speed can correspond to a high particle temperature, but this does not make interplanetary space feel like a hot atmosphere. Temperature describes the average energy of the individual particles, while density describes how many particles are present. A small number of energetic particles carries far less total heat than a dense gas at the same measured temperature. This distinction allows very thin plasma to be described as extremely hot, while still transferring little energy to a solid object. A spacecraft passing through the solar wind is struck by charged particles, yet the total number of impacts is small. Sunlight usually contributes far more to the heating of exposed spacecraft surfaces than the surrounding plasma does. The solar wind shapes electrical and magnetic conditions, but it does not form a warm bath around the planets. Magnetic fields also fill interplanetary space. The sun's rotating magnetic field is carried outward by the solar wind, forming a broad structure that curves through the solar system. Charged particles follow and cross these fields in complex ways. The fields can guide particle motion and store energy, but they do not behave like warm material. They influence plasma without filling the vacuum with dense matter. Dust adds another small component, tiny grains released by comets, asteroid collisions, and other processes drift along paths around the sun. Some grains are no larger than particles of smoke, others are larger fragments that may eventually enter a planetary atmosphere as meteors. Their total mass is small compared with planets and moons, and the distances between individual grains are usually enormous. Each dust grain interacts directly with sunlight. A dark grain absorbs energy and warms. A bright grain reflects more light and may remain cooler. The grain also emits infrared radiation into space. Its temperature settles according to its size composition, rotation distance from the sun, and balance between absorbed and emitted energy. The vacuum around it does not force nearby grains to share the same temperature. Each particle responds almost independently. This independence appears on larger objects as well. A planet-moon asteroid or spacecraft can possess a temperature very different from the surrounding particles. In a dense atmosphere, collisions tend to bring neighboring objects toward a common temperature. In interplanetary space, that process is weak. A sunlit surface can become very warm, while a shaded surface nearby becomes extremely cold. The empty region between them does little to reduce the contrast. The absence of convection is especially important on Earth, Warm air rises and cooler air moves in to replace it. This circulation carries heat across rooms, landscapes, and the entire atmosphere. In space, there is no dense surrounding fluid to rise, sink, or flow around an object. Heat cannot be carried away by ordinary wind. A spacecraft, therefore, loses energy mainly by emitting radiation, not by warming a surrounding atmosphere. The same condition applies to a small rocky body. Sunlight heats the side facing the sun. Energy moves slowly through the rock by conduction, while the surface emits infrared radiation. If the body rotates, each area alternates between sunlight and darkness. Fast rotation can reduce temperature differences by spreading exposure across the surface. Slow rotation allows one side to remain heated for long periods, while the opposite side cools deeply. Shadow has a strong effect because direct sunlight is the main source of energy for many objects in interplanetary space. A shaded region no longer receives that incoming radiation. It continues to release infrared energy and gradually cools. Since the surrounding vacuum supplies little replacement heat, the temperature may fall rapidly at the surface. The exact result depends on the material internal heat, nearby reflected light, and the length of time spent in darkness. Planets do not warm the empty regions around them in the same way that a fire warms nearby air. They emit infrared radiation, and that radiation travels outward. A nearby object may absorb part of it, but most of the energy continues into space. The vacuum does not trap the radiation or become a heated shell. The energy remains in motion until matter absorbs it. Interplanetary space, therefore, contains many forms of energy without becoming a dense thermal environment. Sunlight crosses it, infrared radiation leaves planets and moons, charged particles stream outward, magnetic fields curve through it, dust grains absorb and emit energy. Yet the region itself holds very little heat because it contains very little matter. The apparent emptiness between worlds is not completely inactive. It responds to the sun, carries particles, and transmits radiation across enormous distances. Even so, its defining property remains scarcity. The planets travel through a vacuum where matter is too thin for ordinary conduction and convection to dominate. Each world and object maintains its own energy balance, surrounded not by warm air, but by a nearly empty expanse that allows heat to leave mainly as light. Within the solar system, the apparent emptiness between planets contains a faint population of gas and dust shaped by the sun. These materials are scattered so widely that they do not form a continuous atmosphere, yet they still absorb light, reflect it, emit heat, and respond to magnetic forces. Their presence gives the solar environment a subtle structure that cannot be seen easily with ordinary eyes. Much of the gas begins as the solar wind. Charged particles stream outward from the sun and spread through the planetary system. Close to the sun, this flow is denser and more strongly influenced by solar activity. Farther away, the particles become more dispersed. Sudden eruptions on the sun can send denser clouds of plasma outward, changing local conditions for hours or days as they cross the paths of planets and spacecraft. The gas remains extremely thin. Even when solar activity becomes strong, the number of particles in a given volume is tiny compared with the amount of matter in Earth's atmosphere. The particles can move at very high speeds, and instruments may describe the plasma as having a high temperature. This temperature reflects the average energy of individual particles. It does not mean the region stores a large amount of heat, because the total number of particles remains small. A spacecraft inside this gas is struck by electrons, protons, and heavier ions. These impacts can charge its surfaces and affect instruments, but they usually transfer much less heat than direct sunlight. The thin plasma cannot surround the craft with a warm layer. Its particles arrive separately, with long empty intervals between many collisions. Thermal contact remains weak, so the spacecraft's temperature depends mainly on radiation. Neutral atoms also appear in the solar environment. Some enter from the space between stars, while others are released from planetary atmospheres, comets, or collisions. Because they carry no electrical charge, they respond differently to magnetic fields. They may travel long distances before being ionized by sunlight or by collisions with charged particles. Once ionized, they become part of the plasma and begin moving under the influence of the solar wind and magnetic field. Dust has a more visible effect when enough of it lies along a line of sight. Tiny grains spread through the inner solar system scatter sunlight and produce a faint glow known as zodiacal light. From dark locations on Earth, this glow can appear as a soft band near the horizon, before dawn or after evening twilight. It reveals that the region between planets is not perfectly empty, even though the dust remains extremely sparse. Most interplanetary dust comes from comets and collisions between asteroids. Comets release gas and dust when sunlight warms their icy surfaces. Asteroid impacts break solid material into smaller fragments. Over time, these grains spread along many orbits around the Sun. Some spiral slowly inward, some are pushed outward, and some are swept into planets or ejected from the solar system. A dust grain may be made of silicate rock, carbon-rich material metal, or a mixture of several substances. Its composition determines how strongly it absorbs and reflects sunlight. Dark grains usually absorb a larger fraction of incoming energy. Bright grains reflect more. Size also matters because very small particles interact with light differently from larger ones. Once a grain absorbs sunlight, its internal energy increases. The grain then emits infrared radiation into the surrounding vacuum. If incoming and outgoing energy become equal, its average temperature settles into balance. A grain closer to the Sun generally becomes warmer because it receives more intense radiation. A grain farther away receives less energy and usually remains colder. This balance can change quickly for very small grains. Their low mass allows a single energetic photon to raise their temperature sharply for a brief period. They then cool by emitting infrared radiation. Larger grains change temperature more gradually. Their greater mass stores more energy, smoothing the response to changing illumination. Rotation also affects temperature. A spinning grain exposes different sides to sunlight, spreading the absorbed energy. A slowly rotating grain may develop a warmer sunlit face and a colder shaded face. Internal conduction may reduce this difference depending on the material. Porous grains conduct heat poorly, while compact metallic grains conduct it more efficiently. Sunlight exerts pressure, as well as carrying energy. The force is extremely small, but it acts continuously. On tiny grains, radiation pressure can alter an orbit significantly. Some particles are pushed away from the Sun, especially when their mass is small compared with the area exposed to light. This effect helps shape comet tails and the wider distribution of dust. Another gradual influence is the Poynting-Robertson effect. A grain orbiting the Sun absorbs sunlight and emits radiation while moving. The combined result causes it to lose orbital energy slowly and spiral inward. The process may take thousands or millions of years depending on the grain's size and distance. Collisions or planetary encounters can interrupt the inward drift before it is completed. Dust grains also collide with one another. Most collisions are rare because the region is so thin, but over long periods they matter. Gentle impacts may alter rotation or shape. Faster impacts may break grains into smaller pieces. The smallest fragments can respond strongly to sunlight and the solar wind, changing their paths more quickly than larger particles. Gas and dust, therefore, form a faint active environment around the Sun. They carry little total heat, yet they constantly exchange energy with radiation. Gas particles move rapidly without creating a warm atmosphere. Dust grains warm individually, cool individually, and follow paths shaped by gravity-light collisions and magnetic forces. Their temperatures belong to the matter itself, while the surrounding vacuum remains too empty to store much thermal energy. Seen closely, the solar system is not a clean arrangement of planets moving through perfect nothingness. It contains a delicate haze of particles spread across enormous distances. Each atom and grain responds to sunlight according to its own size-charge composition and position. Together, they reveal how even the thinnest material can interact with a hot star while leaving the vast space around it profoundly cold. Beyond the outer reach of the solar system, the Sun becomes one star among the many billions that form the Milky Way. The space between these stars is not perfectly empty. It contains thin, gas-scattered dust magnetic fields, energetic particles and light arriving from many directions. This material is called the interstellar medium, meaning the matter and radiation that occupy the regions between stellar systems. It is far more diffuse than any atmosphere, yet it plays a central role in the life of the galaxy. The interstellar medium is not uniform. Some regions contain hot, extremely thin plasma shaped by ancient stellar explosions. Other regions hold warmer clouds of neutral atoms. Denser areas contain colder gas and dust, sometimes gathered into broad molecular clouds. These environments may lie close together on galactic scales while maintaining very different temperatures. Their differences arise from density composition, nearby stars, magnetic activity, and the balance between heating and cooling. In the thinnest regions, individual particles may move with great energy. Temperatures can reach hundreds of thousands or even millions of degrees Celsius. Such values describe the speed of the sparse particles rather than a large store of heat. The density is so low that a solid object placed there would receive only a small amount of energy through collisions. As in the solar wind, high particle temperature does not create the effect of a dense, hot atmosphere. This hot gas often forms after a massive star explodes as a supernova. The expanding shock wave compresses and heats surrounding material, producing bubbles that may stretch across many light years. Over time, the gas radiates energy, mixes with neighboring regions, and gradually cools. Several explosions can combine their effects, creating large cavities within the galaxy. These cavities remain faint because their matter is spread so thinly. Warmer, neutral regions contain more atoms, especially hydrogen, though they are still extremely sparse by earthly standards. Ultraviolet light from stars can remove electrons from atoms, while other regions remain mostly neutral. Collisions between particles, absorption of starlight, and interactions with cosmic rays provide energy. Cooling occurs when atoms and ions release radiation at particular wavelengths. The temperature settles according to the competition between these processes. Dust grains are mixed through much of the interstellar gas. They are tiny solid particles made largely of silicates, carbon-rich material, and frozen compounds in colder regions. Although dust accounts for only a small fraction of the total mass, it strongly affects temperature. It absorbs visible and ultraviolet light from stars, becomes warmer, and emits the energy again as infrared radiation. This faint infrared glow allows observatories to trace material that appears dark in visible light. A dust grain in open interstellar space receives light from many stars rather than from one nearby source alone. The combined radiation is much weaker than sunlight near Earth. Most grains, therefore, remain cold, often only several tens of degrees above absolute zero. Their exact temperature depends on size, composition, location, and the strength of the surrounding radiation field. Small grains may warm briefly after absorbing a single energetic photon and then cool again. As gas and dust gather into a denser cloud, the outer layers absorb much of the incoming starlight. The interior becomes shielded especially from ultraviolet radiation. Less energy reaches the deeper material, so temperatures fall. In dark molecular clouds, gas commonly reaches only around 10 degrees above absolute zero. Dust may remain similarly cold, though the two components do not always share exactly the same temperature when the density is low. These clouds are called molecular because much of their hydrogen exists as molecules rather than isolated atoms. Dust grains help this transformation by providing surfaces where hydrogen atoms can meet and join. The grains also block destructive ultraviolet light, allowing molecules to survive. Carbon monoxide and many other molecules occur in smaller amounts and provide useful signals for astronomers because cold molecular hydrogen is difficult to observe directly. Cooling within a molecular cloud occurs through radiation released by atoms, molecules, and dust. When particles collide, they can transfer energy into rotational or vibrational motion within molecules. The molecules later emit photons and lose that energy. Dust grains release infrared radiation into the surrounding space. If the cloud is thin enough for this radiation to escape, cooling continues efficiently. In denser regions, some radiation is absorbed again, changing the balance. Cosmic rays also enter the clouds. These are high-energy particles moving through the galaxy, many of them accelerated by supernova remnants and other energetic environments. They can penetrate more deeply than ordinary starlight and provide a small but persistent source of heating and ionization. Their influence helps maintain weak chemical activity even in the darkest interiors. The pressure inside an interstellar cloud is not produced by temperature alone. Turbulent motion, magnetic fields, and gravity also shape the material. Gas may flow in irregular currents, collide with neighboring streams, or become compressed by expanding bubbles from nearby stars. Some clouds disperse before forming anything new. Others develop denser regions where gravity begins to overcome internal support. Temperature strongly affects this balance. Colder gas moves more slowly and provides less thermal resistance to compression. A cloud that can release energy efficiently may become denser without heating enough to halt contraction. The interstellar medium, therefore, does more than occupy the distance between stars. It creates the cold environments from which new stars and planetary systems can eventually emerge, although each cloud follows a complex history shaped by its surroundings. Across the Milky Way, light and matter remain linked by a continuous exchange. Stars release radiation into the galaxy. Gas absorbs selected wavelengths. Dust gathers broader ranges of light and returns the energy in the infrared. Hot plasma cools through faint emission. Dense clouds shield their interiors and settle toward lower temperatures. No single temperature describes interstellar space because its material is divided among many conditions. The wide regions beyond the solar system are therefore cold in several different senses. Much of their matter is sparse, so the total heat content is low even when particles move rapidly. Denser clouds are genuinely cold because shielding reduces incoming energy and radiation carries heat away. Through these quiet balances, the galaxy contains both glowing stars and dark clouds, with the great spaces between them governed by the same steady laws of absorption, emission, motion, and loss. Beyond the stars, clouds and galaxies, a faint field of radiation fills the observable universe. It arrives from every direction with almost the same strength, passing through intergalactic space and reaching planets, spacecraft, dust grains, and atoms wherever they exist. This radiation is called the cosmic microwave background. It is not produced by nearby stars or by the present activity of galaxies. It is the cooled remnant of light released during the early history of the universe. The early universe is far hotter and denser than it is today. Matter and radiation remain closely mixed in a bright plasma made of charged particles. Electrons move freely rather than remaining bound to atomic nuclei. Light cannot travel far without interacting with these particles. Photons scatter, repeatedly changing direction many times, so the young universe behaves like a glowing fog. As cosmic expansion continues, the overall temperature falls. After several 100,000 years, conditions become cool enough for electrons to join with nuclei and form neutral atoms, mostly hydrogen and helium. This change is called recombination. The name refers to electrons becoming bound to nuclei, even though the process occurs for the first time in cosmic history. Once neutral atoms form, light interacts with matter much less often. The glowing fog becomes transparent and radiation begins traveling freely across space. That ancient light still moves through the universe. During the long interval since its release, space expands greatly. The expansion stretches the wavelength of the radiation, shifting it from visible and infrared light into the microwave part of the electromagnetic spectrum. Its energy decreases as its wavelength grows. The radiation therefore cools along with the expanding universe. Today, the cosmic microwave background has a temperature of about 2 7/10 degrees above absolute zero. This value describes the characteristic energy of the radiation field. It does not mean that every object in space shares exactly this temperature. A star may be thousands or millions of degrees Celsius in its outer layers. A planet may be much warmer than the background. A shielded dust grain may approach the background temperature, while another grain near a star remains warmer. Each object reaches its own balance according to the energy it absorbs and emits. The background creates a minimum source of radiation that is present almost everywhere. An isolated object far from stars and galaxies still receives this faint microwave energy. If every other source of heating disappeared, the object could cool toward the temperature set by the background, though its actual behavior would also depend on material properties and the continuing expansion of the universe. The radiation is extremely weak compared with sunlight near Earth, but its reach is universal. Sensitive instruments detect the background as a nearly uniform glow. Its spectrum closely matches that of an ideal thermal source known as a blackbody. A blackbody is a theoretical object that absorbs and emits radiation with perfect efficiency. The observed spectrum of the cosmic microwave background follows this form with extraordinary precision. This close agreement shows that the radiation once exists in a hot, dense state, where matter and light remain in thermal balance. The glow is not perfectly even. Tiny temperature differences appear across the sky, usually only a few parts in 100,000. These variations record small differences in density within the early universe. Regions containing slightly more matter exert stronger gravity and later grow into larger structures. Over immense periods, they contribute to the formation of galaxies, clusters, and broad cosmic filaments. The pattern of these variations carries information about the composition and geometry of the universe. Their sizes and strengths reveal how ordinary matter, dark matter radiation, and cosmic expansion influence the early plasma. Measurements show that the large-scale geometry of the observable universe is very close to flat. They also support an age of about 13,800,000,000 years. These conclusions arise from combining background observations with other astronomical evidence. The temperature of the cosmic microwave background changes with cosmic time. In the past, when the universe is smaller, the radiation has shorter wavelengths and greater energy. It is therefore warmer. Observations of distant gas clouds support this prediction by revealing how the background influences atoms and molecules at earlier stages of cosmic history. As expansion continues, the wavelengths stretch further and the temperature gradually falls. This cooling differs from the cooling of an ordinary object. A hot stone loses energy by emitting radiation into its surroundings. The cosmic microwave background cools mainly because the space through which it travels expands. Each photon carries less energy as its wavelength stretches. The number of photons within a fixed volume also decreases as the volume of the universe grows. The radiation field becomes both weaker and colder. Microwave photons pass through much of space without interacting strongly with matter. Some are absorbed or scattered by gas dust stars and planets, but most travel freely across enormous distances. When a detector measures them, it receives light that has been moving since the universe first becomes transparent. The signal, therefore, represents a distant surface in time rather than a nearby physical boundary. Galaxies and galaxy clusters can alter small portions of the background. Hot electrons in clusters transfer energy to some microwave photons, changing their spectrum. Moving matter can create additional subtle shifts. Dust within galaxies emits microwaves that must be separated carefully from the ancient signal. Researchers account for these foreground effects by comparing observations across many wavelengths. The background also explains why cosmic space cannot be described as completely without radiation. Even in the darkest void, light from the early universe remains present. Yet, this universal glow carries very little energy. It provides a cold radiation bath rather than a warm environment. The hot sun dominates the energy balance near Earth because its radiation is concentrated by proximity. The ancient background arrives from every direction, but with an intensity far too low to produce comparable heating. The cosmic microwave background therefore preserves a quiet connection between present space and the earliest transparent age of the cosmos. Its near uniform temperature reflects the cooling caused by expansion. Its tiny variations preserve the beginnings of later structure. Its faint photons continue crossing the universe, surrounding every star and planet with the oldest measurable light, while confirming that a universe filled with radiation can remain deeply cold. Every object in space carries energy within its matter, and every object above absolute zero releases part of that energy as electromagnetic radiation. This outward flow is the main way heat leaves planets, moons, dust grains, spacecraft, and clouds when no dense atmosphere surrounds them. In the vacuum, there is too little material for ordinary conduction or convection to remove much energy. Radiation becomes the quiet path by which warmth travels away. Thermal radiation arises from the motion of charged particles within matter. Atoms vibrate in solids, molecules rotate and move in gases, and electrons shift among available energy states. These motions produce electromagnetic waves. The emitted energy may leave as visible light when the material is extremely hot, but cooler objects release most of it at infrared wavelengths. Human eyes cannot detect infrared radiation, though instruments can measure it with great precision. The amount of radiation released depends strongly on temperature. A warm object emits energy more rapidly than a cool object of the same size and material. As an object cools, the rate of energy loss decreases. This creates a gradual slowing of the cooling process. A surface that begins very hot may lose energy quickly, while the same surface cools more gently as its temperature falls. Material properties also affect emission. A surface that emits thermal radiation efficiently is described as having high emissivity. Emissivity is a measure of how closely a real material behaves like an ideal thermal emitter. Dark, rough surfaces often emit infrared energy more effectively than bright, polished metals, though color in visible light does not always predict infrared behavior. Engineers and astronomers therefore measure materials across the wavelengths that matter for each environment. A planet receives radiation from its star while releasing its own radiation into space. Its temperature changes until the outgoing energy broadly matches the absorbed energy. This condition is called radiative equilibrium. It does not mean every location reaches the same temperature or that conditions stop changing. It means that over a chosen period and across a chosen region, the average incoming and outgoing energy approach balance. A planet closer to its star generally receives stronger radiation and must become warmer before it can emit enough energy to match the incoming flow. A more distant planet receives less and can remain cooler while still reaching balance. Surface reflectivity alters the result. A bright world sends much of the incoming light back into space, while a darker world absorbs more and must emit more infrared energy later. Rotation changes the timing of the process. A surface facing a star absorbs energy while a surface turned into darkness continues to radiate without receiving direct sunlight. If the material stores little heat, its temperature rises and falls sharply. If it stores energy, well, changes happen more slowly. Rock, metal, ice, soil, and gas all respond differently because their heat capacity and conductivity are different. Heat capacity describes how much energy a material must absorb to change temperature. A material with high heat capacity can store substantial energy while warming gradually. A material with low heat capacity changes temperature more quickly. Conductivity describes how readily energy moves through the material itself. A highly conductive body can carry heat from its warm side toward its cooler side, reducing surface contrasts. The Moon provides a clear example of radiative cooling. Its surface receives intense sunlight during the long lunar day. With almost no atmosphere to move energy, the upper soil warms strongly. During the long lunar night, direct sunlight disappears. The surface continues emitting infrared radiation into space and becomes extremely cold. Loose lunar soil conducts heat poorly, so warmth, stored deeper below, reaches the surface only slowly. Small asteroids experience similar cycles. Their irregular shapes create changing patterns of sunlight and shadow. One face may receive strong radiation while a nearby hollow remains dark. As the asteroid rotates, each region alternates between absorption and emission. The timing of this cycle can influence the small force created when thermal radiation leaves the surface unevenly, gradually altering the asteroid's rotation or orbit. A spacecraft also depends on radiative balance. Electronic systems, batteries, instruments, and human activity can produce internal heat. Since surrounding space cannot carry this heat away through air, spacecraft use radiators. These surfaces are designed to emit infrared energy efficiently. Other parts may use reflective coatings and insulation to reduce unwanted absorption from sunlight or nearby planets. Insulation in space works differently from thick clothing in an atmosphere. It does not need to trap warm air. Instead, layers of reflective material reduce the exchange of radiation between surfaces. Multiple thin sheets can reflect infrared energy back and forth, slowing heat transfer. The outer layer still emits energy into space, but the inner components remain more stable. Dust grains radiate according to their size and composition. A larger grain often maintains a relatively steady temperature because it stores more energy. A very small grain may absorb a single energetic photon, become briefly warmer, and then release the energy through a pulse of infrared radiation. Observatories detect these emissions and use them to study dust that remains invisible in ordinary light. Gas cools through radiation in a more selective way. Atoms and molecules do not emit every wavelength equally. Collisions place them into higher energy states, and they later release photons at particular wavelengths. These spectral lines act as cooling channels. In thin gas, the photons escape easily, allowing energy to leave. In denser gas, some photons are absorbed again, slowing the cooling. Cooling can also change the structure of gas. As particles lose energy, their average motion slows. Pressure may decrease, allowing gravity or outside forces to compress the material. Compression can then raise the temperature again. The result is a continuing balance among radiation, motion, pressure, and gravity, rather than a simple fall toward absolute cold. No object cools merely because empty space possesses a low temperature in the ordinary sense. It cools because it emits more energy than it absorbs. The surrounding vacuum allows the outgoing radiation to travel away with little interference. When incoming and outgoing energy become equal, the temperature settles into balance. If incoming energy later changes, a new balance develops. Radiative cooling, therefore, governs the quiet thermal lives of objects across space. Warm surfaces release infrared light, gas emits energy at selected wavelengths. Dust grains glow faintly, spacecraft use carefully designed radiators. Planets and moons exchange energy with stars and darkness. In each case, heat leaves not through a surrounding cold wind, but through light carrying energy steadily outward into the vast vacuum. The coldest natural places in the known universe are not found simply at the greatest distance from the Sun or from any other star. They appear where matter receives very little energy, where radiation escapes efficiently, and where surrounding material provides almost no replacement heat. Some of these environments lie inside dark interstellar clouds. Others exist in permanently shadowed hollows on airless worlds. Their temperatures differ, but each remains cold because its energy balance is dominated by loss rather than gain. Within the Milky Way, dense molecular clouds contain some of the coldest large regions of matter. Their outer layers absorb visible and ultraviolet light from nearby stars. Dust grains scattered through the cloud block much of this radiation before it reaches the interior. The deeper gas therefore rests in darkness, protected from most external heating. Temperatures commonly fall to around 10 degrees above absolute zero, though local values depend on density chemistry, cosmic rays, and the strength of surrounding starlight. These clouds are not completely isolated. Cosmic rays penetrate deep into them and provide a weak but persistent source of energy. Collisions between particles also transfer heat, while molecules and dust release radiation. Carbon monoxide, ammonia, and other molecules emit at particular wavelengths after collisions raise them into higher energy states. Dust grains radiate in the infrared. When this outgoing energy escapes more rapidly than new energy arrives, the cloud remains extremely cold. Some compact regions become colder still. The Boomerang Nebula, a young planetary nebula several thousand light-years from Earth, contains gas measured at about 1 degree above absolute zero in parts of its expanding outflow. A planetary nebula forms when a dying star releases its outer layers, though the name has no connection with planets. In this object, gas expands outward with unusual speed. As it expands, it performs work against its surroundings and loses internal energy, causing strong cooling. The measured temperature of the Boomerang Nebula falls below the temperature of the cosmic microwave background. This does not violate the presence of the background radiation. The rapidly expanding gas cools faster than the faint microwave field can warm it. The nebula also absorbs some of the background radiation, allowing astronomers to detect the colder material as a dark feature against the warmer cosmic glow. Observations indicate that this extreme condition is temporary because the expanding gas gradually changes and mixes with its environment. Cold natural environments also occur much closer to Earth. The Moon has no substantial atmosphere to move heat into shadowed regions. Near its poles, the low angle of sunlight allows the rims of some craters to block direct illumination permanently. Their floors remain dark through the lunar year. These places are known as permanently shadowed regions. Inside the deepest shadows, the surface receives no direct solar radiation. Only weak sources remain, including scattered sunlight, infrared radiation from nearby terrain, energetic particles, and a small flow of heat from the Moon's interior. Spacecraft measurements show that some lunar polar surfaces fall below about -240 degrees Celsius. Certain locations may remain colder than the surface of Pluto, even though the Moon travels much closer to the Sun. The shape of each crater controls its temperature. Steep walls can block sunlight over wide areas. A smaller hollow inside a larger shadow may receive even less radiation from surrounding terrain. The darkest places behave as cold traps. Water molecules and other volatile substances that enter them can strike the surface, lose energy, and remain frozen for very long periods. Observations support the presence of water ice in some polar deposits, though its distribution, purity, and origin vary from place to place. Mercury also contains permanently shadowed polar craters. The planet orbits close to the Sun, and its sunlit surface becomes extremely hot. Yet its axis has very little tilt, so sunlight never reaches the floors of certain deep craters near the poles. Radar observations and spacecraft data indicate that water ice survives there beneath or beside dark, insulating material. The sharp contrast shows again that distance from a hot star does not determine temperature by itself. Illumination, geometry, and energy exchange are equally important. Farther from the Sun, icy moons and dwarf planets maintain low average temperatures because sunlight is weak. Their surfaces may rest hundreds of degrees Celsius below the freezing point of water. Bright ice reflects much of the incoming light, while the remaining absorbed energy is returned as infrared radiation. Some bodies contain internal heat from radioactive decay or tidal flexing, so their interiors can remain much warmer than their surfaces. Comets traveling far from the Sun also become deeply cold. Their mixtures of ice dust and rock release little energy while they remain in the outer solar system. As a comet moves inward, sunlight warms its surface and causes frozen compounds to turn directly into gas. When it travels outward again, activity declines and the surface cools. Beneath the upper layers, material may preserve cold conditions for extremely long periods. Temperature records in natural space environments require careful interpretation. A thermometer placed in a shadow does not simply read the temperature of empty space. Its own surface absorbs radiation, emits radiation, conducts heat from its supports, and responds to particles. Instruments must therefore separate the temperature of the detector from the temperature of the material being observed. Remote sensing often relies on infrared or microwave emission, while direct measurements use calibrated sensors placed on or near the surface. The coldest laboratory temperatures on Earth fall far below those found naturally in nebulae or craters, but they are produced under controlled conditions and within tiny amounts of matter. Natural cosmic cold operates across much larger regions and for much longer times. It arises without refrigeration machines using expansion, shielding radiation and isolation. These environments show that cold is not a substance filling dark places. It is a condition of low internal energy maintained when matter receives little heating. A molecular cloud becomes cold behind layers of dust. Expanding gas cools as its energy is spent. A crater floor remains cold because sunlight never reaches it. Ice survives where incoming radiation is too weak to remove it. Across every example, darkness matters because it limits absorbed energy, while the open vacuum allows thermal radiation to continue carrying energy away. Human exploration of cold space depends on machines that remain stable while surrounded by vacuum radiation, sunlight, and deep shadow. Spacecraft do not simply become cold after leaving Earth. Their temperatures change according to what they absorb, what they produce internally, and how efficiently they release energy. Every mission, therefore, carries a thermal system that keeps instruments, computers, batteries, fuel, and structural materials within workable limits. A spacecraft in sunlight may receive strong radiant energy on one side, while the opposite side faces darkness. Without air to spread heat, these surfaces can develop large temperature differences. Metal conducts some energy through the structure, but conduction alone cannot always protect delicate equipment. Engineers use coatings, insulation, heaters, radiators, sun shields, and controlled orientation to manage the flow. Reflective outer surfaces reduce the sunlight absorbed. White paints, polished metals, and special films send much of the incoming radiation away before it becomes heat. Darker surfaces may be chosen where efficient emission is needed. The same material can behave differently in visible and infrared light, so each coating is tested for both absorption and emission. Many spacecraft are wrapped in multi-layer insulation. This consists of thin reflective sheets separated by small gaps. Each layer reduces the exchange of infrared radiation between the spacecraft and its surroundings. The material often appears bright and metallic, but its purpose is thermal. It slows both heating and cooling, allowing internal systems to remain closer to a chosen temperature. Radiators perform the opposite task. They provide surfaces from which unwanted heat escapes as infrared radiation. Electronics generate heat whenever they operate. Batteries warm during charging and discharging. Scientific instruments, communication systems, and computers add energy to the spacecraft. In vacuum, surrounding air cannot carry this heat away, so radiators face cold space and release it directly as light. Some missions also use electrical heaters. A spacecraft traveling far from the sun may receive too little sunlight to keep certain components warm. Fuel lines, batteries, moving mechanisms, and instruments can fail if they become too cold. Small heaters switch on when sensors detect falling temperatures. Their energy may come from solar panels, batteries, or radioactive power sources. Orientation provides another form of control. A spacecraft can turn a reflective shield towards the sun and keep sensitive instruments in shadow. Some observatories maintain a fixed direction, so their cold side remains protected from direct sunlight, Earth and the Moon. The geometry creates a stable thermal environment without requiring large amounts of active cooling. The James Webb Space Telescope uses this method on an especially large scale. Its layered sunshield separates the warm spacecraft side from the cold telescope side. Sunlight, Earthlight and moonlight remain largely on one side while the mirrors and instruments face deep space. The shield reduces incoming heat so strongly that much of the observatory cools passively to only a few dozen degrees above absolute zero. Passive cooling means that heat leaves without a powered refrigeration system. The telescope emits infrared radiation until it approaches a balance with the weak energy reaching it. This low temperature is essential because the telescope studies infrared light. A warm telescope would produce its own infrared glow, which could overwhelm faint signals from distant galaxies, cool stars, planets, gas and dust. One instrument aboard the observatory requires still lower temperatures. A mechanical cryocooler removes heat and brings part of the instrument to only several degrees above absolute zero. A cryocooler is a refrigeration system designed for extremely low temperatures. It transfers energy away from the detector so the instrument can measure faint mid-infrared radiation with reduced interference from its own warmth. Other space telescopes use stored liquid coolants. Liquid helium has often served this purpose because it can maintain instruments at very low temperatures. As the helium absorbs heat, it gradually boils away and escapes. The mission may continue after the coolant is exhausted, but only instruments able to operate at warmer temperatures remain useful. Many infrared detectors become more sensitive when cooled because unwanted electrical motion decreases within the material. Reduced thermal noise allows the signal from incoming light to stand out more clearly. X-ray instruments, microwave receivers, and particle detectors may also use cooling to improve precision. The required temperature depends on the detector and the measurement. Extreme cold can create mechanical problems. Materials contract as they cool, but they do not all contract by the same amount. A mirror support frame cable and adhesive may change size differently. Uneven contraction can bend surfaces, loosen joints, or misalign instruments. Engineers select materials with compatible properties and test complete systems inside large vacuum chambers before launch. Lubricants present another challenge. Ordinary oils may freeze, evaporate, or contaminate nearby optics. Moving parts, therefore, use special dry coatings, selected greases, or designs that require little lubrication. Motors and bearings are tested across repeated cycles of heating and cooling to confirm that they continue moving in vacuum. Spacesuits form small thermal systems around human explorers. The suit protects the body from vacuum while controlling heat created by metabolism. Layers reduce radiation exchange, and a liquid cooling garment carries warmth away from the skin. Water flows through narrow tubes and transfers energy toward equipment that removes or releases the heat. The suit must prevent both overheating in sunlight and excessive cooling in shadow. Robotic landers face similar contrasts on planetary surfaces. A lunar lander may endure intense sunlight during the day and severe cold during the long night. Some missions survive through insulation and heaters, others operate only during the illuminated period and become inactive when darkness arrives. Rovers on Mars use stored electrical energy, internal heaters, and insulated compartments to protect essential systems during cold nights and winters. Thermal instruments aboard these missions measure the environments they cross. Infrared cameras map surface temperatures without physical contact. Radiometers measure the intensity of emitted radiation. Thermometers placed in soil gas or spacecraft structures record local conditions. These measurements reveal how quickly surfaces warm, how deeply heat penetrates, and how much energy leaves after sunset. Human exploration, therefore, depends on controlling the same balance that governs natural objects. Sunlight adds energy. Internal systems create heat. Shadows reduce incoming radiation. Surfaces release energy into space. Every successful mission survives by guiding these flows rather than resisting cold as an invading substance. The machines remain functional because their materials, shields, heaters, radiators, and instruments keep energy moving at a controlled and measurable rate. Scientific understanding of temperature in space rests on measurements that are often indirect. No instrument can touch every distant cloud, star, planet, or region of vacuum. Instead, astronomers study the radiation that reaches telescopes, the particles detected by spacecraft, and the physical effects produced when matter interacts with light. These observations provide a detailed picture, but every conclusion depends on the sensitivity of instruments, the accuracy of models, and the limits imposed by distance. Temperature is usually inferred from radiation. A warm object emits a characteristic range of wavelengths, and the shape of that emission reveals how energy is distributed within its matter. When an object behaves approximately like a blackbody, its temperature can be estimated with high confidence. Many planets, stars, and dust clouds, however, are not perfect thermal emitters. Their surfaces and gases absorb and release selected wavelengths more strongly than others. Scientists must therefore separate the effects of temperature from the effects of composition, texture, density, and geometry. Dust provides a clear example. A cloud may contain grains of different sizes and materials, each responding differently to the same radiation field. Small grains can heat briefly after absorbing individual photons, while larger grains remain closer to a steady temperature. A telescope may receive the combined infrared emission from all of them. The measured signal is real, but converting it into one temperature requires assumptions about the grain population. Observations often indicate a range of temperatures rather than a single value. Gas introduces further complexity. In very thin plasma, particles may not share one common temperature. Electrons can move with one average energy, while heavier ions move with another. Collisions are too rare to bring them rapidly into equilibrium. A measurement based on one type of particle may therefore differ from a measurement based on another. Both can be correct because they describe different parts of the same sparse environment. Astronomers also distinguish between kinetic temperature and excitation temperature. Kinetic temperature describes the motion of particles. Excitation temperature describes how atoms or molecules occupy different internal energy states. In dense matter, these quantities often approach the same value. In thin interstellar gas, radiation and rare collisions may affect the internal states differently, so the two temperatures can diverge. Scientists compare many spectral lines to determine which interpretation best matches the observations. Distance reduces spatial detail. A nearby planetary surface can be mapped at high resolution, while a distant cloud may appear as a single faint patch containing several regions mixed together. Warm outer layers, cold interiors, embedded stars and foreground dust may all contribute to the same beam of light. Higher resolution improves the separation, but even the most powerful telescopes cannot reveal every small structure. Models are used to estimate how much hidden variation remains. The coldest environments are especially difficult to measure because they emit very little energy. Instruments must be cooled so their own thermal radiation does not overwhelm the signal. Detectors must also distinguish faint cosmic emission from radiation produced by Earth, the atmosphere, the spacecraft, and the telescope. Calibration becomes essential. A small instrumental error can produce a large uncertainty when the source itself is extremely weak. Measurements of the cosmic microwave background demonstrate both precision and limitation. Its average temperature is known with great accuracy, and its tiny variations have been mapped across the sky. Yet the signal must be separated from microwave emission produced by dust gas galaxies and charged particles within the Milky Way. Different observing frequencies help identify these foregrounds. The remaining maps are highly reliable, though small uncertainties persist in the removal of contamination and in the interpretation of the finest details. Spacecraft measurements offer direct evidence, but only along limited paths. A probe records particles and fields at its own location. Conditions may change over minutes, hours, or years, and a single trajectory samples only a narrow region. Several spacecraft can reveal broader patterns, but interplanetary and interstellar space remain too large for complete direct mapping. Scientists combine local measurements with remote observations and numerical models to reconstruct the larger environment. The behavior of the solar corona remains an active area of research. Observations show that the corona reaches temperatures far above those of the visible solar surface. Magnetic waves, reconnection turbulence, and small bursts of energy all appear to contribute to the heating. It remains uncertain how much each mechanism contributes in different regions and at different times. The broad physical picture is established while the detailed distribution of energy continues to be investigated. Similar uncertainty applies to the thermal history of gas between galaxies. Much ordinary matter in the nearby universe is difficult to observe because it is spread through thin, warm, and hot filaments. X-ray and ultraviolet observations reveal portions of this material, yet not all of it can be measured directly. Simulations indicate where much of the gas should lie, but the exact temperatures, densities, and chemical states across every filament remain incomplete. Dark matter presents a different limit. It influences galaxies and clusters through gravity, but it does not emit or absorb ordinary light in the way normal matter does. Scientists, therefore, do not measure its temperature by thermal radiation. Some models describe the motion and energy distribution of dark matter particles, but the nature of the particles remains unknown. Observations firmly establish the gravitational effects attributed to dark matter, while its microscopic properties remain uncertain. Dark energy creates an even broader boundary of knowledge. Observations indicate that cosmic expansion is accelerating. The simplest description treats dark energy as a constant property of space, but its physical origin is not known. It affects the long-term cooling and expansion of the universe, yet it is not a form of ordinary heat. The connection lies in cosmic evolution rather than local temperature. Scientific knowledge advances by narrowing these uncertainties without hiding them. Measurements are repeated with different instruments, independent methods are compared, models are tested against new observations, and conclusions are revised when evidence requires change. The result is not a complete map of every temperature in the cosmos, but a strong framework explaining how matter absorbs, stores, transfers, and releases energy. Within that framework, the central facts remain secure. Empty space contains too little matter for ordinary conduction and convection. Radiation carries energy across the vacuum. Objects warm when they absorb more energy than they emit and cool when the balance reverses. The details vary across stars, planets, gas dust, and cosmic background light, while the underlying laws remain consistent across the observable universe. Space remains cold beside a hot sun because light matter and temperature are not the same thing. The sun releases energy continuously, but most of that energy travels outward as radiation through regions containing very little material. The vacuum does not absorb and store sunlight in the way that rock, water, air, or metal does. It serves mainly as the path across which energy moves from one object to another. The sun itself is hot because it contains an enormous amount of matter. Under great pressure, deep in the core, nuclear fusion converts hydrogen into helium and releases energy. That energy moves through the solar interior, reaches the visible surface, and escapes as electromagnetic radiation. The temperature of the sun belongs to the plasma that forms the star. It describes the energy carried by particles within that dense material, not the condition of every empty region touched by its light. Once radiation leaves the sun, it spreads across an ever-growing area. Close to the star, a small surface intercepts a strong flow of energy. Farther away, the same total output is distributed across a much larger sphere. The intensity, therefore, decreases with distance. Even where sunlight remains strong, however, it does not warm empty space directly. It warms matter that absorbs it. A planet becomes warm because its surface and atmosphere receive radiation and convert part of that energy into internal motion. Atoms vibrate more strongly, molecules move more rapidly. Oceans, land, clouds, and gases store and redistribute the incoming energy. The planet then releases infrared radiation back into space. Its average temperature settles according to the balance between absorption and emission. An airless moon follows the same rule with fewer ways to move energy. Its sunlit surface absorbs radiation and becomes warm. Its shaded surface continues emitting infrared energy and becomes cold. With no substantial atmosphere, conduction through the ground and radiation from nearby terrain provide only limited transfer. The contrast between light and shadow becomes severe because the surrounding vacuum does not carry heat from one region to another. A spacecraft experiences a similar division. Sunlight heats exposed panels while shaded components radiate energy away. Engineers do not treat space as a uniformly freezing fluid. They calculate every source of incoming and outgoing energy. Reflective coatings reduce absorption. Insulation slows radiative exchange. Heaters replace lost energy. Radiators release excess warmth. The spacecraft survives by managing radiation rather than by resisting a surrounding cold substance. Thin gas complicates the language of temperature. Particles in the solar wind or hot interstellar plasma may move at speeds corresponding to very high temperatures, yet so few particles are present that they deliver little total heat to a solid object. A dense gas at the same particle temperature would transfer far more energy because collisions would occur continuously. High temperature and high heat content are therefore not identical. Cold interstellar clouds show the opposite condition. Their matter is denser than the surrounding galactic medium, but dust blocks much of the starlight that could warm the interior. Molecules and grains emit radiation that escapes into space. Cosmic rays and weak internal processes provide some heating, yet the balance can remain close to only several degrees above absolute zero. The cloud is cold because its particles hold little average internal energy. The cosmic microwave background adds a faint radiation field throughout the universe. Its temperature is about 2 7/10 degrees above absolute zero. This ancient light prevents the cosmos from being completely without radiation, but its energy density is extremely small compared with sunlight near Earth. It provides a universal background rather than a warm atmosphere. Radiation, therefore, connects hot and cold regions without forcing them to share one temperature. A photon can leave the sun, cross millions of kilometers of vacuum and strike a grain of dust, a telescope mirror, or a planetary surface. Until absorption occurs, the energy remains in transit. The space along the path does not become a reservoir of heat merely because light passes through it. This difference between traveling energy and stored energy resolves the apparent contradiction. Heat is energy moving because of a temperature difference. Temperature describes the energy distribution within matter. Radiation can carry heat across a vacuum, but the vacuum itself contains almost no particles to develop an ordinary temperature. Objects within it reach their own temperatures according to how they interact with incoming and outgoing radiation. The dark appearance of space follows related principles. Sunlight becomes visible when it enters an eye or detector, or when matter scatters it toward an observer. In a nearly empty region, there are too few particles to scatter much light. The beam crosses the darkness unseen until it reaches matter. Space can therefore contain streams of radiation while still appearing black. Cold also does not mean the absence of all energy. Interplanetary space contains sunlight, charged particles, magnetic fields, infrared emission, and microwave background radiation. The total environment remains thermally sparse because the matter capable of holding and exchanging that energy is scarce. A single energetic particle may move rapidly, yet the empty volume around it contributes almost nothing. Across every scale, the same laws remain consistent. Stars produce energy within dense matter. Light transports that energy through vacuum. Planets, moons, dust gas, and machines absorb selected portions. Their temperatures rise or fall until emission balances absorption. Shadows cool because incoming energy decreases. Bright surfaces remain cooler by reflecting light. Dark surfaces often warm by absorbing more. Distance weakens radiation by spreading it across larger areas. Thermal conditions throughout the cosmos emerge from these local exchanges rather than from one universal surrounding temperature. Every surface cloud particle and world responds to the energy available at its own position. The sun and cold space therefore belong to one continuous physical system. The sun is hot because its matter contains and produces immense energy. Space is cold because matter is sparse and radiation rarely remains stored there. Between them, light travels freely, carrying energy without turning the vacuum into a warm substance. The contrast is not a failure of heat to leave the sun. It is the natural result of how heat moves when almost nothing lies in its path. Across the wide darkness, the sun continues to shine with steady power. Its light moves outward through the solar system, crossing regions where matter remains thin and scattered. Planets, moons, dust, and spacecraft receive small portions of that energy, each responding according to distance, material motion, and shadow. The vacuum does not gather the sunlight into a warm ocean. It allows the radiation to continue. Where light meets matter, energy may be reflected, absorbed, stored, moved, and released again. A rocky surface warms beneath direct sunlight. A crater floor cools in permanent darkness. A planet holds energy in its oceans and atmosphere. A grain of dust glows faintly in infrared light before returning its warmth to space. Far beyond the planet's cold gas drifts between stars. Dark clouds shield their interiors from bright radiation. Ancient microwave light passes through the universe with only a trace of its former heat. Every region settles into its own quiet balance between energy arriving and energy leaving. The hot sun and the cold cosmos remain parts of the same natural order. The star holds dense matter, powerful pressure, and continuous fusion. The surrounding space holds very little material at all. Heat can cross that emptiness as radiation, but it does not remain there unless matter absorbs it. The apparent contradiction fades into a simple pattern. Stars shine, light travels, matter responds, warmth gathers briefly within planets, clouds, machines, and dust, then departs again as radiation. Around these islands of matter, the great vacuum remains dark, thin and cold, carrying energy onward without becoming warm itself.